start recording now the exercise. So welcome to the first exercise session. My intention here is to go through the workflow for the how to use the digital place and route tool, so that then you can continue on your own after that. So let's see how to start. I will give an instruction about this in Zulip. Again, I wonder, is Ruslan here? No, he did it already. But anyway, there is one mistake in the first issue. It instructs to push the master branch to the new origin. The correct branch is version 1.0_RC. I will merge it to master, so the instructions are then up to date, but apparently I haven't done that yet. So anyway, I will do it immediately after this, after I have finished this exercise, so then you can proceed with the instructions during this session and get it right away. So to start the first exercise, I use now Veikko's issues because I don't have these issues on myself. But so when doing the preparations, just go through what is said in the issue. These two things for the SSH config. This is mandatory. Then these settings are up to you. If you don't have proper terminal settings, the working might be difficult. This provides you them if needed. But anyways, if you want to work with some other editor, it's fine with me. The thing is that where this actual stuff starts is this part. So you should create this home directory and you should clone this project into that directory with a given URL. So I did that now in vSpace, and I can just give you the. So I created this directory, then I seeded there. And I cloned it now on name elect course 2025 because I have multiple instances. So basically I'm working now in that directory. Then I changed the origin with these commands: git remote rename origin old. So I have the old origin as old with name old, and I added a new origin with this command. So this is now the URL of the project that those issues have been attached to in your GitLab. So I can show it on here. This is the project. So you get the URL by just clicking that one and then finding it from here. And once we have done that, we are ready to proceed with the instructions. So it says cd to that directory and change the remote origin. Okay, I did that already. Push the master branch to new origin and remove the old origin if not removed. So if you want to play it safe now, what I did is that I checked out the version 1.0_RC and pushed it to the origin master. But I will, as said, I will merge this to the master branch, so then you can follow the instructions literally. But just to be certain, I won't do it now. Then we run a couple of commands: init submodules.sh. This initializes all the submodules in your project. If you get errors about not able to access something, most likely your vSpace SSH key is not provided in GitLab or to GitLab, or you are missing some SSH key somewhere, but most likely it's in GitLab. So this uses SSH to handle these submodules, and all the subprojects, if I recall correctly, are currently either in Bubba GitLab or in global GitLab, and you need to have SSH keys in both of them. Then let's see what happens if you source me. It gives you a couple of instructions, so you need to provide this command. This sets some of the tools, and then you need to provide this command. This is not absolutely mandatory, but let's do it. It provides you the analog design environment. Now we are working in the digital domain, so after that, actually, yeah, skip that place. It has same commands, but okay, we do the same things here. Yeah, this takes into use the tools. So we go to SPI slave, and then we give these commands, but those commands are also in the top level. So just to be sure, I can run them again. Okay, so if you don't get any errors, we are all set, and then we can proceed with the simple exercise. So we initted the submodules, we have source to source me, then we give the command configure/b. And this B, what it does, it disables the LSF cluster submissions because our LSF cluster is not available for this machine. Without that, your make will fail. So remember to give that when you configure. Just waiting the configure to go through, so I will then continue with that. Okay, so now the configure went through, and then we are ready to test this with make. So running the make. This takes a while to execute, so I will go through the rest of the files why it does it. And this is the first step of the exercise to execute, because and it will be executed just to debug your environment. If you can't go through this phase, you can't do any of the exercises. So your tool setup really don't work. This is the pipe cleaning phase of the design environment. It's kind of a no-brainer to synthesize with the given scripts the SPI slave, but it really efficiently tells you if there is something off with your system setups. So meanwhile it runs, I will show you the files to edit in case when you need to go through the flow. So okay, I have some flow here tested, so I probably can show you how it goes. Once we have this once the flow has been run through, we can open it with make debug Innovus. Okay, and then we can give command GUI show. Opens the graphical user interface, and we can read the DB by looking for file dbs postroute.enc. Okay, and then we can check from the graphical user interface. It should look about this. So now what we can do with this, every time you press F, it gives you the full zoom. So if you have zoomed in or out, you can always return to full view by pressing F. Then if you want to check the different layers, now I removed visibility of all the layers. I can click them on one by one, like metal 1. Now we can see that there are lots of metal 1 rails here. And then we can keep on adding metals and layers like this if we wish. So this is to make the visual inspection of the layout in the end of the flow. You can also check couple of other things. This is quite nice clock tree debugger. Okay. So we have very simple clock tree. For the more complex designs, you may have tens of clocks and lots of clock paths. This is very simple design. So basically what we are checking here is that we just have a clock buffer. So basically it's driving all the clock pins with a single inverter, which is fine in this case because our clock specification is very loose. But this is how you debug the clocks. So this is actually the main thing that you can check for the functionality of the layout is ready once you have synthesized your own microcontroller. But now back to the actual workflow and how to use that. So I will close this Innovus now. So when you are doing your own design eventually, what you first do is that you go through the configure file and you check what is there. And I will now identify the places that you need to edit when you are doing the work. So now assume that you are doing the implementation of your own microcontroller. So these parts, tech root, PDK home, you don't need to touch. You don't need to touch these flow variables. No need to touch this design definition paths, but this you must edit when you change the name of your module. This is the name of the top module that you are synthesizing as it is given in your Verilog file. So when you're doing your own design, you must change the module name. Then there is a list called linked Verilog, and here you must provide all the Verilog source files in the order you wish them to be compiled. So we see here that SPI slave uses async set register, so async set register must be given first. Like top of the list is compiled first. And then no need to change these macro repositories, no need to list analog macros if you don't have them. We get back to this in next session. And these you don't need to edit either. Then we have flavors for different threshold voltage flavors of the semiconductor process. If you stick with HVT, at least that has been debugged multiple times. But HVT means that your standard cells leak less. SLVT, if that exists in the process, it gives you super low threshold voltage, which means that your cells are extremely fast, but they also leak a lot. So you have some kind of a static power consumption even in CMOS logic, because you basically you may have tens of thousands or hundreds of thousands of logic cells between your supplies, and all the transistors leak a bit. So if they leak a nanoampere and you have billion paths in between your supplies, you are already consuming 1 ampere even though the circuit does actually nothing. So this is how the effect of the threshold voltage in the power consumption of the circuit. But now that's focusing on how to get the flow through, so this HVT is fine. No need to touch these. No need to affect this either or change this either. Here, if you need to do some kind of a preparation for your design, you can do it here. It says create top level Verilog, but as you see, there is an if clause with 2 cases, and then set of commands that prepare some design, in this case the SPI slave, but if you have some kind of a preparations that you need to do for your designs, you just script it here. So it will be automatically executed every time you run the configure. And here, this preparation happens to add some Verilog files, so we append them to the linked Verilog on the top of the list. So, but to remember, this part just configures your Verilog sources, whatever. If needed. Then rest of this stuff here, no need to touch, but one of the files that you definitely need to edit is the SDC file. So there are two things that you absolutely need to edit. One is your module name and the related Verilog files in this linked Verilog, or there is also VSDL files variable. So if you are using VSDL, you need to provide the VSDL files there. And then the SDC file, because this is dependent on your pin names of the design. So the structure is relatively simple. There are a couple of variables, master clock period, which is now 10, and slow clock period, which is also now 10. These are nanoseconds. The time unit is nanoseconds in this case. Then we create a clock. This is standard way of creating clock signals for the digital flow. You can change the name as you wish, but in many cases, there is no need to change the name. But what is important is that you need to assign it to a port of your design, and this port must exist. So if your clock pin or port name is something else than clock, you need to put it here. Then there is another clock that has been defined in this section. Then some commented stuff, but the important part is that I set the input delays for all the inputs, which is 1/10 of the clock period. And then input transition for all the inputs, which is now 1 nanosecond. You need to change this if you want to have it smaller, or if you change the clock frequency. But like 1/10 is relatively 1/10 of the period is some kind of a rule of thumb that I often have used in these templates. Then for the outputs, I set the output delay. This is kind of an extra timing margin that you reserve at the output for extra delay that you may have in the circuit. And then 15 femtofarad capacitance for capacitive load for all the outputs. So that was the SDC file. And you can check these if you want to change. These should reflect the values that you define above, but most of the time no need to change it for these simple designs. Then we are not running conformal verification in this flow on this course, so no need to touch here. And these libraries have been defined already, so no need to touch them. No need to touch this MMC config file. And then we have some default variables for logic synthesis defined here. Most often you don't need to touch these either. These are usually, if you want to preserve some hierarchy, you edit the part where it flattens the cells, which is this part. But now all of the things here have been commented, but if you want to set that some parts are not flattened in logic hierarchy, you need to provide this set db ungroup OK false structure. And then rest of the file you don't need to touch. I will go through the required settings where you actually use the analog macros during the next exercise, and I show you how to use those macro instances as a part of your flow next exercise. But now this is just to go through once the basic settings for the flow. Then the workflow itself. We can usually you run the flow up to a point where the synthesis has been done, and you try to run the floor plan. So you would run a command make to floor plan. And most often, first time that fails because there is something off in your floor plan and you need to edit that part. So first of all, how to get there or how to debug that is that you make debug innovus. And you open the GUI. And in the first step of floor plan, it creates a file called pre-fp.enc. This is created in a very early phase of the floor plan, so basically nothing in the floor plan phase except the design reading has been performed in this. Sorry, read db. Okay. And then we can see what is in the GUI, so basically nothing. And now we should check what to edit. So open your favorite text editor. There is one file that describes the structure of the flow. It's called it's in flow scripts design config.tcl. And this shows all the steps that are in the flow. And now the floor plan is performed in a step init floor plan, and what it says that it sources a file that is in design scripts path named initfloorplan.tcl. And this file is in directory design scripts. This design scripts directory has lots of tcl scripts, and if we open this basically all these tcl files that are referred by this design config.tcl, they are located in this design scripts directory. So we can open this init floor plan file from there. Design scripts, I will put this visible, see it better. Design scripts init floor plan.tickle. And now you have this init floor plan.tickle file. We can debug the thing by just sourcing these couple of first lines, let's say up to this point, and just pasting them here. And now we see that here it writes the db pre-fp.enc. So this is the file that we just opened. So no need to write it again, and we can continue from here. So if we want to debug the flow, we just paste command by command and see what happens in the graphical user interface. Okay, it altered the floor plan a bit because there was a command create floor plan. Then we delete the power intents. This defines how the supplies are connected, or they are allowed to be connected, but we have only one supply, so this barely has effect in this design. It's not also visible in the layout in any way. Then there is a first script that we actually execute. So now you see that this init floor plan already, it calls many scripts. So in this case, it's quite handy to be able to split your editor in two or use tabs or whatever, and then open the file here. So what was the name of the file? Create floor plan. And we see that it sources some variables and then runs a command that creates the floor plan with some arguments defined in this common vars.tickle file. You can check what is there, but basically all these variables here, they are defined in a mechanism that is described in this configure file that you edited in very beginning. So you can check what variables are available here and use them in your scripts, but it has variables floor plan X, floor plan Y, IO to core, okay, 4 times IO to core. So we can run these commands. Fplan X and IO to core are given in configure as variables. You can set them there, but what they define is the dimension of the floor plan and what is the distance from the IO to the actual core area. Your design most likely will be smaller than this, or it may be bigger than this, depends on how you have configured your microcontrollers. So you may need to change the aspect ratio and the IO to core. You change them in configure, and then you can, when you get to this point, you can test it. Or here, you can actually give the numbers here and test what would be the nice aspect ratio if you want to modify it. But now we have executed a subscript create floor plan step by step by opening the file and pasting that to the command line. And this is the way how you can debug the individual commands during the flow, because there will be hundreds of them and it's very easy to make a mistake. So the next script will be commit power intent. It's given at this page, really doesn't change anything. It's also related to power domains of the design. Then next, place IOs. We can guess what happens there. So what I have done is, again, sourcing variables just to be sure that they are sourced. Then this structure, what it is, it figures out the direction of the metal tree. There are two ways to configure the semiconductor process. One is that the third metal is vertical. The other one is that the third metal is horizontal. And usually digital designs are done in a way that if metal 3 is vertical, metal 4 is horizontal, metal 5 is vertical. So all odd metals are vertical. if metal 3 is horizontal or odd metals are horizontal, and that affects how you arrange or what layers you should use for routing. So this figures out the direction of the metal tree. It's automated for you, and then placed on that, it assigns the layers to the left, right, and top, bottom, or bottom, top. So let's see what happens. Let's first run the variables, then we can do interesting. Yeah, so it was the command of this, let's say this bottom top pin that it put it out. But if we can also check this metal tree direction, it's so metal tree is horizontal, and we figured it out with this this line, and then depending on that, it sets the pin directions. Okay, we have run this, so now we are ready to actually place the pins. If your or when your designs have other pins, you need to change the pin names. So this is just a list of all your pins and where you would like to have them. The other thing is that you should use this fixed pin equals 1, because if you don't, you just do the initial placement of the pin, but the tool has a freedom to move them wherever, which is a bit weird, because usually if you place something, many times you want that to be there. But if you forget this fixed pin, it just places the pins, but the tool can move them around the circuit as it likes. So I just was contacted by one of our PhD students that why my pins doesn't stay where I put them, and the reason was that he was missing this fixed pin equals 1 option here. So let's see what happens if we run this. Now the pins are here. We can zoom in to see how they look like, but so basically they are small pieces of metal, and this yellow arrow, it really doesn't exist. It just shows the direction of the pin, and then there is also the name of the pin here. This is IO monitor in 4. And yeah, now this is easy. This has some 20-ish pins that you need to place, but you could have hundreds of them, and then figuring out how to order them and put them where you want this might be tricky. So what this does is that it starts from the center. For example, this first command, spread type center, means that it starts from the center on the left side of the chip. Fixed pin, so you can't move them. Spacing is 10 micron spacing. Layer defined by this, and then the list of pins. Only problem that this may cause is that if the center is some fraction of the coordinate, all of your pins are like off coordinate, but most of the cases it's not severe problem. If you really want to control accurately the stuff, you give the coordinates where to place the pin. But more control you need, more script you need to write. So in some cases, if it works and it's good enough, then use the higher levels of abstraction. If you need more control, then be more specific. Then, okay, this is how to place the IOs. Then we can check what is the generate floor plan. Okay, this does nothing at the moment. It seems that I have fixed the typos. Also, there are many of them in this file, I remember, but now I have fixed it. Good. Then place ports. So this file is kind of redundant to this place IOs. Sometimes we need actual cells, like IO cells, to put on the layout. So I have divided them to two scripts, but now we don't have this cell, so everything in this file has been commented out. This is kind of an example that this is, if you have bad cells, you can place them like this. Then there is a file that has been commented out, but sometimes you need to cut out regions from your floor plan, and this is done with these do row cutouts.tcl. We can check what is there, but if I have it, I don't. It is deleted, so that's the reason why it doesn't exist. Anyway, there are commands how to create notches into design. Basically, you cut out regions from the core, so you do that in that file. Then define routing rules. This is a file that defines some special rules for clock routing. Clocks are special nets. They are a bit sensitive because if your clock doesn't work, your chip doesn't work. And because they synchronize everything, they are a bit sensitive to variation of capacitance and resistances. So rule of thumb, coming from outer space based on the good understanding of, or legacy understanding of the digital designers, is that you route the clock with double width and double spacing. It reduces the interclock net interference and gives you a bit less variation on the capacitances and resistances of the clock network. And you don't need to touch this file. We can just see what happens if we execute that. And it gives you, first it defines the widths and spacing, so, or extracts the widths and spacings of different metal layers, and then it sets the routing rules to be double of that. Then we have command finalize floor plan. Let's see what it does. You can also check what is there. Okay, it just snaps the floor plan to the grid if needed. Basically doesn't do much, but a step that is good to do. And then we write a file prestripes.enc. We can rewrite it like here. So now we have done all the preparations, and next we do the part that is the most time consuming and error prone, so it's good to save the design before it. And the phase where we are going is creating rings and stripes, which is basically majority of your supply chain routing, like VDD and VSS. So let's see, it's an design scripts, create rings, stripes, yes. Okay, so this file has 204 lines, not that much, but this may be also way more complex if you have lots of blocks that you need to handle differently. Again, we source some definitions. This usually does nothing, just defines variables. Then we print some layer information that might be useful when you design the script. This prints out directions and minimum pitch, minimum width, and minimum spacing of all these metal layers. And also this gives an example how to extract these values, because if you want to do something as a function of minimum width, for example, it's very handy. If you define any routine in your routing script, it makes it process portable because it scales. New processes have different values of minimum width and minimum spacing, so you can write your scripts to be process portable, at least partially process portable. By the way, also these metal names that I use, these are variables, and there is one file where these values for these variables are defined. So if I write the scripts using these metal layer variable definitions, it doesn't matter what is the actual name of the metal layer. You can always, the script is portable. So I can show it here. It's a file. Process dependent configs and helpers, and there is process variables. So here it is. Variables that you can use for routing. And for this process, they are named metal 1, metal 2, and so forth. But for example, in some more advanced nodes, this metal 3 is actually what CA1, and then metal 4 is CA2, and so forth. So the naming can be whatever, but with this we map them to predefined variables. So that was the information. Then we set here again the metal 3 direction. Later on we can make decisions based it. Okay, and then there is a command add end caps. I show what it does. So that is somehow important information. So if it did anything, it did. End caps. First cells that are placed here are the end of the rows. This is where the power routing eventually gets connected to, and if we want to see what is inside the cell, we need to click it open and then click all the layers visible, also the pins. So it shows that in this end cap we have two very small pieces of metal, one named VDD and the other named VSS. Those are your row supply connections eventually. Then we need to add special cells called well taps. If you remember from basics of IC design, if you have done it, all the transistors, the substrate is in some well, P well or N well, and if defined, those well taps are placed with this command. Now it seems that this well tap cell is empty, so these standard cells have the well tap connection built in. But if they don't, then this cell must be defined and it is used to provide this well connection. We delete all the previous routing, and then we set some routing top and bottom layer variables. No need to touch these during this project. And we are ready to go forward. This sets the routing layer directions and variables based on this metal 3 direction. And then the first actual routing phase, we add core rings. And now we can see what it actually did. It created a ring around a core with multiple metal layers. So if you check the layers, usually there is nothing with polysilicon or contacts, but okay, and metal one we don't use for those rings, so we see only those pins. Vias are used to connect to the metal, so but this is the first one. Metal 2 ring, vertical. Metal 3 horizontal, via connecting them. Via 3 connects to metal 4. Metal 4 is vertical. Via 4 connects to metal 5. Metal 5 is horizontal, and so forth. So we have a ring of metals around the core. And then the next step would be lots of variables that are observed to be good, related to what kind of a vias we use and what kind of a what is the bottom routing layer and what is the distance from block for the routing and so forth. But no need to control those in this project. And then we connect those rings to the actual cells. You see that, okay, it created metal 1 shapes, 281, and then created 562 vias. And this is quite important step. Now you see that this black area here was empty. Now it's filled with the blue metal ones. And these row endings are connected to the rings that go around the actual circuit. And we can continue with the script. And then something that is called stripes. So now we have the rings around the neck, the core. We have connected the rails to the rings that go around the core. But this connection is still relatively weak. Even though there is lots of metals, this metal one is many times very resistive, and there is only connections at the end of the rows. So we can do better. And how we do it is that we lay over vertical and horizontal metal rails for power routing only. And those are called stripes. And now it creates them with for each loop. So we need to be careful what we paste, and it's relatively long for each loop. So it ends here. And then we can paste it. This may take a moment. Now we have a lot more metal over our chip. So horizontal and vertical lines with a constant spacing width and interval are placed both horizontally and vertically over the whole chip. This is the way how you usually do the power routing in digital chips. And the way I have determined this is that I make an educated evaluation about how much of a circuit area must be sacrificed on each layer to power routing, and then based on that information I set the width and the spacing of these wires. These wires also have the maximum width and maximum spacing, and you can play around with that. But with this default setting, most of the stuff in this process goes without any problem for you. So you can use the same values. And then, as said, there are two top layers that will be routed. So these are figured out by trial and error once when I set up this process. So let's see what happens with the top. Usually the top two layers, they have a bit different width and spacing rules than the other layers. So that's the reason why they are handled as a special case. So it added two layers more to the routing. So at this point, the circuit is empty. It has only pins in place, and it has a huge mesh of metal to provide the supply routing for the design. And then in the very end of this create rings and stripes, it just basically deselects everything and sets some variable back to its default value. So now we have done this. And what we are ready to do is write a final version of the floor plan in case we want to return and check the result after the flow has been executed. So that is the floor planning phase, and rest of the flow you don't need to touch. But next week we will check how to place some macro instances in this floor plan. But the first week's exercise, the only intention is that go through this, understand how to paste those scripts into this Innovus command window, see how the layout changes, think of what if I need to change something, how would I do that? And then you can start to gradually map that to your coming design of your microcontroller. Any questions at this point? I'm happy that it worked, because usually there might be some kind of a demo effect when going through this, but this time no. Let's see. I had this one flow running in the background. Yes. So it says flow ran to completion, so it means that everything is good. You may see something like this. Currently we don't care. So this is the point where how to say, experience gives you confidence that some errors you need to care about, some errors you probably don't. And my observation is that most of the time when this flow runs to completion, everything is fine. And if it does not run to completion, then you really need to start debugging. There are a couple of errors that you need to check. And one of those is this clock tree debugging to see whether you have a clock tree or not. Not having clock tree is a bad thing. It's harmful. One more thing I could show you. There is let's see where it was. Yeah. There is a branch called VHDL version, and you can check it out to see how the VHDL designs are configured. But the only difference is that now instead of linked Verilog, we provide linked VHDL. And the script that actually reads in the VHDL code is written in a way that it determines whether you have Verilog or VSDL and reads, based on that it reads in the files. I can check. If I remember, there was some problem with the versioning of VSDL, but I can check it now from here if that is a problem and needs to be fixed. It is design scripts, init designify. Yeah, this read HDL in this design scripts may need a version flag like -2008 in order to be able to read in the newest versions of VSDL. I'm not certain about that, but if you encounter problems, let's get back to that. I can also check it once I get to my desk. Yeah. So this seems to work now. Any questions at this point? Tommy, did I forget something? Okay, so now if you want to try, we can go through the exercise. Now we still have like 45 minutes to try to complete the first exercise and see how it goes. Okay, I will stop recording now because there is nothing more to show to recorded audience. Thanks for watching so far.